Hello and welcome back. Welcome to our second lesson in this Unit 6, which is about scaling, shifting, and combining random variables. So we talked last time in the last lesson about what a random variable is. It's basically a probability distribution, usually a discrete probability distribution. So today we're going to look at describing the effects of linear transformations, so scaling, shifting, multiplying, adding numbers, on parameters of random variables. So how does it affect the mean and standard deviation when I add, subtract numbers, multiply numbers, etc. So just as a warm-up, if I were to find the expected value or mean and then the standard deviation of this probability model, I'm going to give you a second, maybe pause the video, see if you remember how to do this, and then I will go ahead and show you the answer and the formula. So for expected value or mean, we do each number in the table times its probability, and we add those all together. So 60 times 0.2 plus 70 times 0.3, etc. And that gives me a mean or an expected value of 74. And then for standard deviation, there we go. Had a little bit of an issue there. So standard deviation, we would first find the variance, which is what goes in the square root. So each number minus the mean, so 60 minus 74 squared times its probability 0.2. And then 70 minus 74 squared times 0.3, etc. We add those all together, that gives us the variance. And then we take the square root of that to get our standard deviation, which is 9.165. So that was our quick warm-up on what we learned in the last lesson. So now let's look at what happens when we shift and scale that data. So here's our original table. And there was our mean and standard deviation of that original table. So the question I'm first going to ask is what happens if I were to add 50 to each value in that table? So on the top row, I just add 50 to all of those numbers. So then my table becomes this. My probability stayed the same, but I added 50 to every number on the top row. So the question is, what happens to the mean and what happens to the standard deviation? And you may think about what we talked about in the last semester at some point about scaling and shifting and how things get affected. So if I were to find the mean of this data, the mean would increase by 50, which kind of makes sense. If I'm increasing each x value by 50, it would make sense that the mean would also increase by 50. But what about standard deviation? So if you remember from last semester, think about when we're adding a number, is we're basically just shifting it to the right or to the left. But that in and of itself is not necessarily going to make it more or less spread out, which is what standard deviation is measuring. So the standard deviation would stay the same. The other way you can think about it is if I think about the formula I use in this type of problem to find standard deviation, right? Over here I'm doing 60 minus 74 squared times 0.2. And over here I'm going 110 minus 124 squared times 0.2. 110 minus 124 is the same as 60 minus 64. So those differences between each value and the mean have not changed. So the standard deviation doesn't change. So let's look at what happens. Same thing, I'm going to go back to my original data, but now I'm going to multiply each value by 3. That's scaling. So adding a number or subtracting a number is shifting. Multiplying by a number is scaling. So if I multiply by 3, this is my new table. Just as you might expect, the mean gets multiplied by 3. All of these numbers got 3 times bigger, so it makes sense that our mean would also get 3 times bigger. But what about standard deviation, right? Shifting didn't change standard deviation. What about scaling? So scaling, if you remember from last semester, we're multiplying every value by 3, and things do get a lot more spread out because we're multiplying each value by 3. Smaller numbers times 3 and bigger numbers times 3, that's a big difference. So in this case, standard deviation is going to get 3 times bigger, right? And if we go back to formula, right, 60 minus 74 squared times 0.2, and then 180 minus 122 squared times 0.2, that's a much bigger difference between each value and the mean. So it does end up being a much bigger standard deviation. So we're going to talk about just kind of the basics of what we found out in rule format. This might be a good thing to write down on notes in terms of what the rules are if you need that. So for shifting, right, adding or subtracting a constant affects mean, but not standard deviation and variance. Remember, variance is just standard deviation squared. So in other words, that rule looks like this. Now this is a lot more like formulaic version of that rule, but it's saying the same thing, right? E meaning expected value of a variable plus or minus a constant just is going to be the original mean of that variable plus or minus that same constant. Whereas the variance and standard deviation of a variable plus or minus a constant is going to just be the original variance and standard deviation of that variable. Right? So again, it's really just saying the same thing as this, just in a formulaic version. And then our scaling rule says when we multiply by a constant, that is going to affect mean and standard deviation and variance. So mathematically, formulaically, this is how, formulaically, I don't know if that's a word. This is how that works out. So expected value or mean of a number, a constant times a variable is just going to be that same constant times that original mean. For standard deviation, it's the original constant times the standard deviation. The way that works out for variance is it's going to end up being that constant squared. Right? If I think about the standard deviation is the constant times the original standard deviation. If I square that to get the variance, the A also gets squared. And we'll kind of see in a little bit how that might affect in real life situations. So our first example, we're going to look at just a really not specific, out of context, just very vague set of information and practice finding the new or changed mean and standard deviation. So x and y are two independent random variables with the following attributes. So e of x, or the mean of x, is 11, standard deviation of x is 9, mean of y is 24, and the standard deviation of y is 5. So if I wanted to find the mean and standard deviation of these new transformed variables, so for part A, 3x, so 3 times x, we're multiplying by a constant, we're scaling. So the mean of 3x, when we multiply by a constant, the mean also gets multiplied by that constant. We're just going to do 3 times the mean of x. 3 times 11 is 33. Easy cheesy. Standard deviation of 3x. Standard deviation is also affected by multiplying by a constant. So we're just going to do 3 times the original standard deviation. 3 times 9, 27. Not too bad. Part B, y minus 15. So we are taking the variable y and we're subtracting a constant. We're subtracting 15. So for mean, or expected value, when we subtract a constant from our variable, we know we can just subtract that same constant from our mean. So e of y, or mean of y, minus 15. 24 minus 15 is 9. For standard deviation, the rule for shifting, which is what I'm doing here, when I subtract or add a constant, standard deviation is not affected by that. So the standard deviation of y minus 15 is just going to be the same as the original standard deviation of y. That minus 15 is not going to affect that standard deviation. So it's just going to stay what it originally was, which is 5. So let's look at some more rules and do some more examples. So now let's look at what happens when we combine random variables. So we have 2 variables, x and y, and we are thinking about either adding them or subtracting them or combining them in some way. So our first rule is what happens with mean. So the mean of x plus or minus y is just going to be the mean of x plus or minus the mean of y. So in other words, you can just add or subtract their means the same way we add or subtracted the variables. Not too tricky. So the thing about mean, the expected value, a little saying that I have sometimes, is that the expected value, which is the mean, the expected value always does what you expect it to. So whatever it is that you're doing to the variables, we know that the mean is going to be added or subtracted or multiplied or whatever in the same exact way. So expected value always does what you expect it to. Variance and standard deviation are not as straightforward for several reasons. So, firstly, know that in order to do any kind of combining of separate random variables, the standard deviation and variance, the only way I can find those values is if I know that those two variables are independent, right? Mean is just looking at kind of that center of the distribution. It's okay to do the mean even if the two variables are not independent. That's just telling us what to expect with that combination. But variance is a lot more trickier, or standard deviation, that variability. If the two variables are affecting each other, the variability is uncertain. So know that in order to do this kind of combination for standard deviation and variance, we have to know that the two variables are independent. If they're not independent, or if we don't know they're independent, we cannot determine the variance or standard deviation of that combined variable. So that's one thing to keep in mind. The other thing is that you'll kind of notice in here, it's a little bit of trickiness involved. Variance is a little bit more straightforward. I can just combine the variances. So the variance of x plus or minus y would just be the variance of x plus the variance of y. But standard deviation is a lot trickier. I always say we can't just add standard deviations because the way we calculate standard deviation involves a square root. So just adding them straight is not really allowed. It's kind of like square root of 5 plus square root of 5 is not just square root of 10. We can't just do that. We have to put them both under the square root and then add them and then re-square root them. So we have to be careful with how we deal with standard deviation. We have to kind of deal with it a little bit differently. And I'll give you another analogy that I use for that later. But the other thing that you may have noticed is that these formulas both have a plus in it. And that is because when we are combining variables, the variability, the standard deviation, the variance always increases, even if we're subtracting the variables. And let me explain why, and then we'll get to some examples. So why do we always add with variance or standard deviation? So we're going to talk about dogs because everybody loves dogs. Maybe not everybody, but a lot of people. So here's a German Shepherd. Here's a poodle. For the sake of argument today, we're going to say that the weight of German Shepherds ranges from 75 to 95 pounds. So if I represented that kind of with a number line, 75 is on the low end, 95 is on the high end, right? If we wanted to think about that in terms of like a mean or a center and a variability, 85 is in the middle. So 85, give or take 10 pounds is what that would be. I don't know why the 10 is not showing up. Hold on, we're going to pause. Okay, I made it show up. So 85, give or take 10 pounds is basically what we're saying is the weight of a German Shepherd. Poodles, for the sake of argument today, weigh anywhere from about 40 to 50 pounds. So our poodles distribution goes from 40 to 50. So we'll say it's 45 pounds, give or take 5 pounds. So if I wanted to know what is the combination of a random poodle and a random German Shepherd's weight. So if I have two random of animals of each of those breeds and I wanted to know their combined weight, on the low end of that combined weight would be 75 plus 40. They both weighed the absolute least. The high end of that weight, 95 plus 50. The high end of that weight, so 145 pounds. The middle of that is 130, give or take 15 pounds. So if I notice my mean 85 plus 45 is 130, 10 plus 5 is 15. So when I add the random variables, mean and variance kind of react in the same way. They both get bigger, which makes sense because we're adding them. Of course it would. But let's look at what happens when I subtract them. If I wanted to know the difference between the weights of a random German Shepherd and a random poodle. So again, I'm going to think about what's on the low end of that difference and on the high end of that difference. So initially you might be like, oh, 75 minus 40 is going to be the low end. But remember, we're talking about kind of what is the smallest difference in weights that I could get between any German Shepherd and any poodle. So if the German Shepherd weighed 75, we had a really small German Shepherd, and our poodle weighed 50, we had a really big poodle, then the smallest difference that I could get in their weights is 25. Similarly, and the biggest difference in their weights would be if I have a really big German Shepherd, so a 95-pound German Shepherd, and a really small poodle, so 40-pound poodle. That gives me a difference of 55. The middle of that set of differences is 40 plus or minus 15 pounds. So 40 plus 15 is 55, 40 minus 15 is 25. So my mean decreased, 85 minus 45 is 40. Right? My mean went down, that makes sense. But my standard deviation or my variability still went up. So any kind of combination of two variables, each with their own variability on their own, when I combine them, it's always going to lead to more uncertainty. Right? It's more variability because of the fact that I'm combining them and they're each coming with their own variability. So I'm always going to add when I'm dealing with variance. So let's look at some examples where I'm dealing with this adding and subtracting and combining situation. So first, same numbers as before. Part C, I'm going to do x plus y. So I'm adding x and plus y and finding the new mean and standard deviation. All right, so expected value or mean always does what we expect it to. I'm just going to add them together. So e of x plus e of y, 11 plus 24 is 35. Not too bad. Expected value is easy. Standard deviation, however, is a little trickier because firstly, I cannot just add standard deviations. I can add variances, but then I have to work back to the standard deviation. So what we're really doing is I'm adding the variance of x plus the variance of y. And remember, variance is standard deviation squared. So variance of x would be standard deviation of x squared, 9 squared. Variance of y would be 5 squared. So I can add the variances, but then that still gives me the combined variance. So to get back to standard deviation, those added is 106, by the way. To get back to standard deviation, I have to take the square root of that number, which is 10.3. So if I look at this formula here, square root of 9 squared plus 5 squared, it might kind of remind you of something you did back in geometry in the day. So I sometimes call this kind of combining variables standard deviation rule, I kind of call it the Pythagorean theorem of statistics, right? When I'm talking about a right triangle and I have like one side is 3, one side is 4, and I want to know how long the hypotenuse is, I can't just do 3 plus 4. Right? Because that's not how distance formula works. I have to do 3 squared plus 4 squared and then square root it. It's a similar idea with this. It's for different reasons, but it's a similar concept. So again, I call this the Pythagorean theorem of statistics in terms of how we add standard deviations. For x minus y, again, expected value always does what we expect it to. So I'm just going to do mean of x minus mean of y. So 11 minus 24, which is negative 13. Yes, I can get a negative number for a mean because I'm talking about the difference between two variables. If x has a bigger mean than y, when I subtract them, that difference is going to be negative. Right? So you can get a negative number for a mean. That is okay. Standard deviation of x minus y. Right? Again, I can't just add or subtract standard deviations. I have to deal with variances. And if you remember what we just talked about with the poodles and the German shepherds, when I'm combining two variables, the combined standard deviation always needs to be added. So same as what we did last time, I'm going to do the variance of x plus the variance of y and then square root it. And because these are the same standard deviations as my previous one, it's going to actually work out exactly the same as x plus y did. So the standard deviation of x plus y is the exact same as the standard deviation of x minus y. Right, we saw that with the German shepherds and poodles example too. Now let's look at one where we are combining the same variable multiple times. And a little bit later in the lesson, like towards the very, very end, we will talk about like what this would mean or look like in real life. But for now, we're just being a little bit out of context. So x1 plus x2 plus x3 means that we are combining the variable x with itself 3 times. You might be thinking, isn't that just the same as multiplying by 3? It's not, and I'll explain why later. But when it's written like this, when we have a variable that's kind of written out like this in this format, we're going to treat this with the combination rule and not with the scaling rule. So expected value always does what we expect it to. Expected value is going to turn out the same way anyway. So I'm just going to do e of x or mean of x plus mean of x plus mean of x. 11 plus 11 plus 11 is 33, which is the same thing I get when I multiply 3 times 11. So with mean, it's not going to make a difference. It works out the same way, whether I use the scaling rule or the combination rule. But with standard deviation, it's a little different, because if I was scaling, if I was doing 3x, then I know I could just multiply my standard deviation by that same constant. But because I'm treating with this with the combination rule, I have to deal with, I can't just add standard deviations, I have to add variances and then square root it. So it turns into what we did on that last couple of examples. So I can add the variances 3 times, variance of x plus variance of x plus variance of x, and then square root it to get the standard deviation. So 9 squared plus 9 squared plus 9 squared, square rooted. It's the square root of 243, which is 15.6. Whereas if I had done it with scaling, 3x, 3 times 9 would be 27. So it's a different standard deviation when I am looking at this in a different way. And again, I will show you in a minute about why, in a real life example, how scaling would be different from combining in this way. All right, last example with this set of data, 5x minus 3y. We're doing some scaling, some shifting, some combining all in together. Mean of x, expected value, always does what you expect it to. It's going to be pretty easy. We basically can just kind of plug in the mean of x and the mean of y into that equation and just do the math. So mean is always going to be easy. 5 times 11 minus 3 times 24, which comes out to negative 17. Straightforward, easy, mean is easy. Standard deviation is tricky, especially on one like this where we are doing some of a little of both. We have some scaling and we have some combining that is happening. Firstly, remember that even though we're subtracting these random variables, when we deal with the combining of the variances, we have to add. We always increase standard deviation or variance, even if we're subtracting the 2 variables. But in terms of the scaling, that still acts the same. So what we end up doing, right, is I'm kind of thinking about the scaling first. If there's scaling, it should really happen first. It's kind of like order of operations. I would do the multiplication before I would do the adding and subtracting. So the same thing happens here. In this situation, I would deal with that multiplication with that scaling first. All right, so I can think about, and actually this is wrong, so I'm going to fix this. Okay, so this is what it should have been. So first we do the scaling. We can do 5 times the standard deviation of x and 3 times the standard deviation of y. It's still wrong. Pretend that says y. I'll fix it in a minute. So I can do that first because we would do scaling first. That would give us the new standard deviations of 5x and the standard deviation of 3y. Now when it comes to the combining part of it, right, we always add, so we have a plus, but then we know we have to add the variances in order to do this because we can't just add the standard deviation. So that's why I'm squaring them, right? So I do the scaling for each variable, I square them to get their variances, and I add them to get the combined variance. And then I'm going to square root it to get the standard deviation. Right, so we end up with 5 times 9 squared plus 3 times 5 squared, and then square rooted that, which gives me, that shows up on the bottom, about 47.4. Right, so when we have that combination of things happening, we kind of want to follow order of operations. So in this case, the scaling came first, then the combining, and then we do the square root to get back to standard deviation, right? I'm going to fix that to y real quick. Okay, it's fixed. So we're going to do another example, but I'm not going to kind of go through it. I just want you to have a chance to practice so you can deal with all of these rules. So here is a new set of data. We have mean of x, mean of y, standard deviation of x, standard deviation of y, and then I've given you kind of several things that you can practice with in terms of finding those combined standard deviations. So if I were you, I would pause the video, work on these on your own, and then come back to see if you get the right answers. If there's any ones that you are confused about or not sure about, then what I would do is kind of put a star by them so that you can ask me a question about it in class next time. So here are our answers. Hopefully you got all the means or the expected values correct, because the expected value always does what you expect it to. Expected value or mean is easy. But some of the standard deviations you might have had some issues with. So if you did, make sure that you let me know. Put a star by them. Either come into tutorials or we'll talk about it in class next time. So now I want to look at a couple of kind of more real life examples where we talk about why scaling is not necessarily the same as adding the same variable twice with the combination rule. So let's look at an example. Here is a probability model showing amounts of money you could win at a dice game. This is from the last lesson example towards the end. So we have you could win $0, you have a 25 out of 36 chance, you can win $50 with a 5 out of 36 chance, or you could win $100 with a 1 out of 6 chance. If I find the mean and standard deviation of that random variable just using our rule, to find that, the mean is 24 and the standard deviation is 38. So the average amount of money you win of this game per play of the game is $24 with a standard deviation of 38, which kind of tells us there's a lot of variation here. So what would be the mean and standard deviation of the amount of money I won if, part A, what if I double the amounts of money that I could win? So instead of 0, 50, 100, I now make it 0, 100, 200. So if I multiply or double the amounts of money that I win, that's basically scaling. That's what we mean by scaling in a real life situation, because that's literally me doubling the numbers in the table. So 0, 100, 200, when I find the new mean and find the new standard deviation, it's going to work like our scaling rule. So mean of 2x would be just 2 times the original mean. 2 times 24 is 48. Standard deviation of 2x, I'm just scaling, so I can just multiply the standard deviation by 2. So 2 times 38 is 76. So that's scaling. Part B, what if we play the game twice without changing the original dollar amounts? So playing the game twice, that's an example of a combination of the same variable twice. So I'm not actually changing the numbers in the table. So we're not scaling, we're playing the game twice, which represents that combination of variables. So expected value pretty much works out the same. E of x, or mean of x plus mean of x, 24 plus 24 is 48. The mean's going to work out the same as what we did on part A. But standard deviation is where things are going to be different, because if you remember, if I'm combining variables, which is what I'm doing here, I cannot just add standard deviations. I have to add variances, right? So I end up doing standard deviation squared, so 38 squared plus 38 squared, and then square rooting it to get 54. So my standard deviation changes when I'm combining versus just scaling, right? The other note I wanted to make here, I have a little star. The standard deviation part would only work assuming that each play of the game is independent. So it can't be a game of skill where you get better. It would have to be a complete game of chance where I don't change my probability of winning from one play to the next. That's the only way I could find that standard deviation. And then just to make the point, what if I were to play the game 200 times? What would be the total mean and standard deviation of the total amount of money that I could win playing the game 200 times? So we're playing the game, we're not scaling, we're not multiplying the money amounts by 200. We are playing the game 200 times, assuming that every play is independent. So my mean pretty much does what you expect it to, 24 plus 24 plus 24 plus 24 plus 24, 200 times. Would basically just be 200 times 24, which is 4,800. But standard deviation, right? I can't just add standard deviation, so I can't just do 38 times 24. I have to add variances. So 38 squared plus 38 squared plus 38 squared plus 38 squared plus 38 squared, 200 times. So basically 200 times 38 squared gives me that variance. And then square root that, we get about $537.40. So that's an extreme example of combining variables. A lot of variables. All right, so that is, oh, I forgot there's this one last example. I was about to say that's it, but there's one more example and then we'll be done. So the mean weight of a red delicious apple is 9 ounces with a standard deviation of 0.75 ounces. An online gift store sells gift box containing 5 red delicious apples. At the time of packaging, 5 red delicious apples are randomly selected and packaged in a box. So what are the mean and standard deviation of the total weight of 5 apples? So when I think about combining this, I have to think about, okay, am I scaling? Am I multiplying by 5? Or am I combining and adding together 5 times? So I always like to use an example like this to explain the difference in another way. So we kind of saw in the last example what the difference was. In this case, scaling, multiplying by 5 would be like, I have a red delicious apple that's 5 times as big as a normal apple. What's the mean and standard deviation of that? That would be scaling, but that's not what's happening here. We don't have a gigantic apple. We just have 5 apples. So when we deal with the combination, we are doing, we are going to be doing the x1 plus x2 plus x3 plus x4 plus x5. Right? So I'm going to give you a minute to think about that, and then I will put the answers for this last example in a little PDF that you can check your answers later. Part B, the combined weight of packing material and box is always 10 ounces. So it's constantly, that packing material and box is 10 ounces, constant. What are the mean and standard deviation of a complete gift box? So 5 apples plus a constant of 10. Okay. So now we're doing some combination because we have 5 apples, and then we're adding a constant of 10. So think about how adding a constant affects mean and standard deviation. And then part C, suppose that the weights of red delicious apples are approximately normally distributed. What's the probability that a complete gift box would weigh more than 60 ounces? I just added in a normal model situation. So what do you think we're going to use? This is actually what we're going to learn in the next lesson. So don't worry too much if you're not sure. But if you have an idea, try that out and see what you think. I will put the answers to this last example, at least part 1 and B, in a little PDF so that you can check your answers in a little bit. So there you go. It'll be attached in the comments below or on this page somewhere eventually in the slideshow. I'm going to stop talking. Have a good day, guys. Bye.